Hello everyone, this is the second of two lessons that I have for you on nuclear reactions. In the first one, I talked about the two different broad categories, nuclear fission and nuclear fusion reactions, and I also touched on the three different kinds of radiation that you need to know about for this course. That's the alpha, the beta, and the gamma radiation. Talked a little bit about balancing nuclear reactions. I'll also do that in this lesson, along with the main focus, which is calculating the amount of energy that is released through nuclear reactions. So the big draw is really, the amount of energy that is released. So compared to traditional forms of energy that we use to generate electrical energy, fossil fuels, of course, many drawbacks associated with the fossil fuels, the pollutants that are put into the atmosphere leading to acid deposition, carbon dioxide, contributing to global climate change. So we're really trying to eventually eliminate our use of fossil fuels in terms of generating electrical energy. Other traditional forms, wind energy, wind turbines, water or hydroelectric. But with nuclear energy, huge amounts of energy that are released and can be used to generate electrical energy in nuclear generating stations compared to these other more traditional forms of generating electrical energy. So how much more? Well, really, we're talking about 1,000,000 times more energy using the nuclear reactors that we have today, which are nuclear fission reactions, compared to combustion reactions. So if we talk about using coal in order to generate electrical energy and compare that to using uranium, the fuel that we do use in nuclear fission reactors, including our Canadian CANDU reactor, 1,000,000 times more energy for the same amount of moles that we do have using fission compared to combustion. And if we can ever get this figured out, nuclear fusion reactions, again, those are the reactions that do take place in our sun, even more, up to 100,000,000 times more energy. Right now, as I speak, they are building in Europe a demonstration nuclear fusion reactor, and it is at a cost of somewhere on the order of $25 billion to build this one. And again, that is just going to be a demonstration facility to determine if it is feasible to actually go ahead and generate energy through nuclear fusion. And this would be ideal because with our nuclear fission reactors, we do have radioactive waste that is generated that does need to be stored for long periods of time. And in the case of nuclear fusion, if we could figure that out, there wouldn't be any nuclear waste that is generated through that. So how can we get this huge amount of energy that is generated through nuclear reactions? Well, it all comes down to Albert Einstein's equation, this equation right here that's in your data booklet, more than 100 years ago. So this is the mass energy equivalency equation. This comes from his special theory of relativity. And what it really says is that these two here, mass and energy, they're interconvertible. So we can take mass and we can convert it into energy. Essentially, the mass disappears and it all is converted into energy, and we can do the reverse as well. So they are interchangeable, they are essentially equivalent, and that's what this equation here says that we are going to be using. So the delta E, delta change in, what we're taking a look is the change in energy. Just like with combustion reactions that we did calculations for using Hess's law, we did take a look at the difference between the products and the reactants, and that's what we're going to do for this calculation as well, only now rather than taking a look at the enthalpy difference, the heats of formation between reactants and products, we're going to take a look at the change in mass between the reactants and the products. So that change in mass, remember that we do have conservation of mass. In a chemical reaction, you have to conserve the amount of mass in the products compared to what you had in the reactants. In the case of nuclear reactions, that is not going to be the case. We can have a change in mass, and that change in mass is what is converted into the energy. C, we've seen before what this lowercase c is. This is the speed of light, and this is a big number. This is the 3.0 times 10 to the 8 meters per second. So really, really big number. And it's not only this number, it's this number squared. So we need to take this and square that, and that now gives us 9.0 times 10 to the 16 meters squared per second squared. So you take a big number like this and even multiply it by a very small mass, and that gives us a very huge number in terms of the amount of energy that is released, energy that can be used to turn turbines and generate electrical energy. So yes, in nuclear reactions, it is the mass that is converted into energy. And this big number here is what results in the big numbers in terms of the amount of energy that is released. So I also have in brackets here, sometimes we can just consider matter of really just being a form of energy, a frozen form of energy that we can tap into. We can essentially get rid of that matter and convert that matter into enormous amounts of energy. So the two different categories of nuclear reactions, the fission and the fusion reactions, I'll talk about both of those. Remember, with fission reactions, what we're doing is we're taking something big and we're splitting it apart. So in the picture that I'm showing you here, what is big is going to be our uranium. So very large number of protons, very large mass number that we do have as well. And we're going to strike it or bombard it with neutrons to kind of get this reaction going. So that's going to lower the stability of the uranium and eventually allowing it to be split apart into the smaller pieces, which are barium and krypton, and some more neutrons. So more neutrons that are being generated is eventually what leads to this being a chain reaction, because we now can have these neutrons bombarding more uranium and just continuing to keep this reaction going. So the key here is that we're taking something big and we're splitting it into things that are smaller. If we also take a look at the reactants that we have here, so for these ones, what we're going to find is that there is a higher mass. Then when we take a look at the products, add up the mass of all of the products, compare it to the mass that we have in the reactants, and we'll find that all of a sudden it has a lower mass. Again, with chemical reactions, this can't be the case. With nuclear reactions, it can be the case because we're taking some of this energy and we're releasing that energy, or sorry, some of that mass, and releasing it in the form of energy, which is typically heat. So this is the reaction that does in fact take place in nuclear reactors around the world, including our Canadian CANDU reactor. And that heat that is released is used to heat up water, boil water, generate steam, create kinetic energy, and eventually use that to turn huge, huge turbines, mechanical energy, connect it to a generator, and generate electrical energy. That is how we use nuclear energy and turn it into electrical energy. So yeah, it's the difference that we're interested in initially, the difference in the mass that we're going to take a look at first of all, between the products and the reactants, and then use that to actually determine how much energy is going to be released in a nuclear reaction. For fusion reactions, this now involves the joining together of smaller masses. So fission, take something big, split it apart. Fusion, take things smaller and join them together to form something that is bigger. So this, of course, is what we did talk about in terms of the thermonuclear reaction taking place in our sun, and that involves different versions of hydrogen. I'll just write them both down here as hydrogen. eventually them fusing together to form the larger element. So hydrogen, those are the two smallest elements, of course, on the periodic table. Helium is the next one, and they join together. And the key is, through this process, we do have energy that is being released. And from the sun, of course, that covers all of the different wavelengths, frequencies of electromagnetic radiation. And what we'll also find as well is that comparing nuclear fusion to fission, there is more energy that you can get from fusion than even from nuclear fission reactions. So again, that's why it would be nice to kind of figure out the nuclear fusion in terms of nuclear reactors. The big problem with these, though, with nuclear fusion and creating a nuclear fusion reaction is that just like in the sun, you need temperatures of millions degrees Celsius. And the problem is we can do that, but you have to put more energy in than the energy that you get out in the end. So you have a negative energy return. So finally, just comparing these two categories of nuclear reactions. So the fusion, two smaller things. So deuterium is one of the isotopes of hydrogen. So that is the one that has one proton and one neutron. And that's why we have a mass number equal to 2, because we have one of each. The tritium, different isotope of hydrogen, still one proton, of course, because it is one hydrogen, but now we have 2 neutrons, so the mass number is 3. So those two combining together are what will form the helium, but what we're really interested in, of course, is the amount of energy that is released along the way. With fission, neutrons striking something that is big, splitting it into things that are smaller. They don't show it on here, but again, we would have a huge amount of energy that is also being released, and that's what we're most interested in. So let's go ahead and take a look at the balancing of nuclear reactions first of all here. So as a reminder, all of this is in your data booklet. I'll in fact go to the data booklet in a second here. Alpha decay, this is our alpha particle, essentially the helium. Beta decay, that is this here. Symbols, this is the symbol for alpha, this is the symbol for beta, and this one here is, well, it's really just an electron, what we are talking about. So I do have here, right, the balanced equation for the alpha decay of this radioactive element here, radium-226. So let's go to the data booklet and let's take a look at the information in the data booklet. This is page 8 in your data booklet. We've taken a look at this before. So a couple of different tables and an equation right down at the bottom that we're interested in. So again, you don't need to remember what an alpha particle is because it's right here. Alpha particle, it is the helium, 2 protons, 2 neutrons, mass number of 4, the symbol for it, and these are numbers that we're going to be using. This is the mass, 4.00151, and yes, you do need to use every single one of those digits, and for every number in this table and the table down below, it's all times 10 to the negative 3. You cannot forget that. It's not just 4.00151, it's times 10 to the negative 3 kilograms per mole. That is the mass for our alpha particle. We also have our beta. Again, the symbol for it, it is an electron, the mass of that. Also on the right-hand side, we have the positron. Gamma radiation, no mass, again with that. Mass of the neutron, the proton, and then a selection of different radioactive elements. So the ones that I'm going to be referring to right here when we do these first calculations, this one is our radium. So it's right here for you, the isotope. Mass number at the top, again, 226. That is the protons and neutrons, and that's where the name radium-226 comes from. The 226 is the mass number, referring specifically to that particular isotope of the radium. Number at the bottom, of course, is the protons, 88 protons from the periodic table for the radium. And we'll see I'm also using this one here. Radon, 222. 86 is the number of protons, 222 is the mass number. And right down at the bottom, we have Einstein's equation, E equals mc squared, and what each of those is representing. Okay, so back to our balancing here for this reaction. So the steps that we do have. So first of all, write down the partial equation. So why do I say the partial equation? Where we're told that we have this. So radium is the fuel. So we just saw from the data booklet, symbol for radium is Ra. It is the 226 for the mass number, and 88 is the number of protons for the radium. What else do we know? Well, we're told that we have alpha decay. So that's going to be one of our products. So we're going to take the radium, we're going to split it apart. We're going to get an alpha particle, which is the helium that we see right here. And now, well, we need to figure out what the other one is. So this is the partial equation that we can get from the problem that you're given. But now we need to figure out what the other product is. And that's where the balancing comes in. So whatever number you have for the mass number in the reactants, that has to equal the numbers that we have on the product side as well. So here we have 4. We have another reactant. Some number plus 4 has to give us 226. Or if we just go 226 minus 4, it tells us that the number here must be 222. 222 plus 4 is 226. That is how you balance nuclear reactions. So same thing with the number of protons, the atomic number. If we go 88 minus 2, or what number plus 2? 86 plus 2 would give us 88. And if you take a look either page 8 of your data booklet or just the periodic table, take a look at what element has atomic number 86, and that is Rn, which is radon. So now what we do have is our balanced nuclear reaction for the alpha decay of the radium. So we're going to use this one for our calculation and determine how much energy is actually produced and released using Einstein's mass energy equivalency equation. So you can do this if you like. You can just square C right away. So 9 times 10 to the 16 meters squared per second squared, or squared in the end. Either way, it doesn't matter. So I'm going to do the calculation for the alpha decay and the amount of energy generated from 1 mole and also from 1 kilogram of that radium-226. And just a reminder, it's all in your data booklet, and you cannot forget this or your calculations will most definitely be wrong. Every number is times 10 to the negative 3. So I'll just write down our reaction again here, so we also have it on this page. So it is the radium-226, 88 protons, alpha decay, which is the helium, and the other product is going to be the radon, 86 for the atomic number, 222 for the mass. So we're going to calculate the change in energy, but what I'm going to do first of all, this is actually going to be, or should be, the delta, is I'm going to calculate the change in the mass. So we're going to take a look at the sum of. Remember, this is the sum of. So I'm going to add together the mass of our 2 different products that we do have here, and then I'm going to subtract the mass of our 1 reactant that we do have. So kind of similar to the calculations that we did again for combustion reactions. And remember, it is products minus reactants that we are doing. So I have some big numbers to kind of squeeze in here. So I'm going to start way over at the left-hand side. So directly from the data booklet, the mass for the helium is 4.00151, and yes, you need to write all of these digits down and plug every single one of them into your calculator. And don't forget, this is times 10 to the negative 3. Units are kilograms per mole. Okay, so that's our first product. I'm going to take the sum of the products, so I'm going to add them together. Let me just put this in square brackets to keep it all together for the products. Now I'm taking a look at the radon. Go to your data booklet, and what you'll find is that the number for this one is 222.0174. 0.57. Make sure you get all these digits in. It might not seem like a big deal when we're going to the 5th decimal point, but when you're multiplying numbers by times 10 to the 16, it is going to make a difference for these calculations. Again, this is times 10 to the negative 3 kilograms per mole. Okay, so now we have our products taken care of. Okay, so that's everything that I have in the square brackets here. So now I'm going to go minus our one reactant, which is the radium, and this one here is 226.02540 times 10 to the negative 3 kilograms per mole. Okay, so initially, just what I'm calculating is not the energy yet, but just the change in mass. So carefully plug all of these numbers into your calculator. You do end up with a negative number because mass is being lost. So it does work out to negative 6.32 times 10 to the negative 6. So this is a really small number. It's not much of a change in mass. It's only a really, really tiny change that we do have here. Okay, so this is our change in mass, but now I'm going to multiply it by the speed of light squared. So that is 3.0 times 10 to the 8 meters per second, and this is all squared. So when you do that, that's now going to give us our change in energy. And that's going to be equal to, again, it is negative, energy is released, 5.688. And when you're plugging these numbers into your calculator, you should save all of the digits until your very final answer before you do any rounding. So I may have rounded it to the 3 decimal places here, but you should always keep all the numbers right until the very end. And this is times 10 to the 11. So this is now a huge, huge number that we do have. And the units for this, if you take a look at all the units in here, it ends up being kilograms times meter squared divided by second squared divided by the number of moles. But in the end, what that does work out to is joules per mole. So this is the amount of energy that is released from 1 mole of our original fuel that we do have, which in this case is our radium. So again, sort of imagining what a mole is sometimes kind of difficult. So now let's just change this and let's say, well, what about per kilogram? And of course, this right here should be 10 to the negative 3. It should be superscripted. So in order to get the amount of energy per kilogram, all we need to do is divide this answer that I have here by the mass per mole of our reactant, which is the number that I already have written above here, the 226.02540 times 10 to the negative 3. So let me go ahead and do that. Again, all of the numbers should have been saved in the calculator until the very, very end. Okay, so a big number here, joules per mole. Writing down the units so you can see what cancels out. We're going to divide that by our 226.02540 times 10 to the negative 3. And this is now kilograms per mole. So now what's going to cancel out for us is the moles. We're left with joules and kilograms. We're left with joules per kilogram. And that works out to negative 2.52 times 10 to the 12. Huge, huge, huge number. And this is joules per kilogram. For 1 kilogram of this fuel, we're getting in a massive number in terms of the joules that are generated. So I'm just going to quickly do the same thing here, only for a fusion reaction. I'll try and speed it up a little bit. So here what we do have is 4 different hydrogen that are fusing together form helium, some electrons, and some gamma radiation. Okay, so this is fusion. It's the four that I'm fusing together. So what we do is we calculate the amount of energy per mole. But remember, these coefficients in front, those are the moles. So this is kind of for 4 moles, but I want to do it for 1. So what I'm actually going to do is just divide each of these by 4. I'm going to divide this by 4. I'm going to divide this by 4. So then what I end up with is this is now 1 mole here. This is, well, just as it shows, 1/4 here. And reducing this, 2/4 is 1/2. Okay, so those are going to be the coefficients. I don't need to worry too much about this because this has no mass, and I don't need to count it in my calculations anyway. So anyway, down below here, yeah, so that's what I'm showing, is the calculation that I'm going to do. So I need to go to the data booklet and find the mass of the proton, the mass of the helium, which we already saw, and the mass of the electrons, and that's what we're going to go ahead and be using for these calculations. So this time I'll just do it all together using the E equals mc squared. I'll get a nice fresh page for us here as well to do these calculations on. Okay, so writing our equation at the top, change in energy equals the change in mass times the speed of light squared. Okay, so starting off with our hydrogen, so I'll just put that at the top so we can keep track that this is our hydrogen or proton that we're going to have here. Oh, sorry about that. No, we're going to start with, not with our reactant, of course. We're going to start with our product that we do have here. So the product is going to be, let's start with the helium that we have. And so we have 1/4. So 1/4, let me just write it over here. I'm going to write it as a decimal. 1/4 is 0.25, just so you know where these numbers are coming from that I'm using. So 0.25, that's going to be my coefficient. And now the mass of the helium, which we saw in the previous question, which is the 4.00151 times 10 to the negative 3 kilograms per mole. Okay, so that's our one product. The only other one that we need to be concerned about is our electron. So our electron that we have here, and -1 for the charge on that one. So we're going to add this one in because it is the sum of the masses in the products. This was our mass for the helium. The mass for the electron, I'll write down as well. But first of all, we need that coefficient, and it was 1/2. And of course, 1/2 is equal to 0.5. So I'll put that in for the coefficient, 0.5. And now I'll put in the mass for the electron. So that is a really, really, really small number, 0.000. Make sure you don't miss a 0 in there. Again, it will make a difference in terms of your calculations. 549. Same thing, times 10 to the negative 3 kilograms per mole. So now I have my two products. I have to write it on a line down below, but I'm going to now subtract our reactants that we had. So I did divide it by 4, so I don't have a coefficient here. It's just 1, so I can just write in the mass for the hydrogen. So this is now the hydrogen or the proton that I'm putting in down below here, and that's the 1.00728 times 10 to the negative 3 kilograms per mole. Now I need my c squared, so I'm just going to write that in here right away as well. So you should add all of these together, add and subtract first, and then multiply by the speed of light squared. So that is our 3.0 times 10 to the 8 meters per second, all of that squared. So plugging all of that into your calculator in the end, what we're going to end up with is negative 5.97 times 10 to the 11 joules per mole of the hydrogen that we started with in the first place. So let's just kind of go back here. Let's compare this number for the calculation that we did for can compare to the fission reaction. Okay, so we have a 10 to the 11. If we compare it to this one here, this one is also 10 to the 11. So how can we say that we're getting more energy from a fusion reaction than from a fission reaction? Well, what I'm going to do with this now is I'm going to divide it by the mass for the proton. So now we can get the energy per kilogram of protons. So that number is just the one up above here. So 1.00728 times 10 to the negative 3 kilograms per mole. Just like with the previous calculation, moles cancel out, and we're going to end up with joules per kilogram. So this is where we're now going to see the big difference. So this works out to 5.93 times 10 to the 14. So this is now 100 times, about 100 times more energy that we're getting from a fusion reaction than from that fission reaction. And yes, this is important for you to remember that from a nuclear fusion reaction, we're getting considerably more energy than from what we're using in nuclear reactors right now, which is nuclear fission.